And so today we are going to give you the overview of what happened in mostly the second half of this class. But before we talk about that, one thing that I do want you to realize is that, most of the time in our learning process, we are so focused on something that's, in front of us in a way that we only look in, if saying that if we are in a forest, right, most of the time when you are learning, you might ignore the fact that we are actually in a forest, but focusing too much on a single tree. So it turns out that you are missing the big pictures. And the purpose of this lecture is not actually teaching you something new, but remind yourself what's the big picture of the class, and to have you figuring out how to use this big picture to more efficiently learn. Or maybe you will figure out that with those big pictures, there's no need for you to memorize or trying to practice specific ways of solving problems. So what's the ultimate big picture of computer architecture is actually this, volume architecture, right? So a lot of stuff that we have learned in this quarter is totally depending on this volume architecture in a way that processor memory storage, right? Is most of the stuff you learn in this lecture, in this class is typical, it's depending on this very basic big picture, right? So with that, right, with respect to that, remember you have program compiled into instructions and data. And when you want to launch a program, it needs some system software, for example, your operating system, to put the program into a specific memory location where your processor would know and get the instruction from the memory, and your processor will look into it, figuring out what the instruction wants us to do. And if the instruction itself additionally requests data from the memory, we would have additional data memory access request. But after we finish this instruction, we are going to fetch another instruction from the memory. So that's the big picture. And with that big picture, right, a lot of things will make sense, right? So for example, why the performance equation looks like that? Because the amount of work that your processor has to do is depending on the total amount of instructions, or say dynamic instances of the instructions that you need to execute. And then how long does it take to execute those instructions? It's depending on how many cycles you need per instructions and how long is each cycle, right? So it's not too difficult for you to right now understand why the execution time of a program is calculated through these three elements. And because the longer the time, the worse the performance. So that's how the performance is derived. And in the first half of the quarter, we have been talking about how to optimize the memory because memory is so slow. But now in the second part of the quarter, we are focusing mainly on how to execute your program. So assume that we have done our best to optimize the memory, and we make the memory performance aligned with your processing speed. Then how can we further make the processing better, right? So that goes back to the big picture of volume architecture, right? So remember, the volume architecture requires us to fetch instructions from the memory, right? So the very first thing that when you want to execute an instruction, you definitely want to fetch the instruction from the memory, and then you have to figure out what instruction wants us to do and prepare the inputs for the functional units that is going to exercise this instruction. So it turns out you have to decode, you have to prepare those register values. And when you want to execute the instructions, depending on what kind of instructions, you may use different parts of your hardware. So for example, for LU instruction, you will have your LU reading those register values and perform operations. Or you might have a conditional branch, which require you to determine a branch outcome, which means that based on it's taken or not taken, you may modify your program counter. And then if it's a memory operation, You have to determine the effective address and then rewrite the memory. And if it's and after you get everything done, right, saying that you get your LU result, you get your memory read result, you want to present that to the register so that later instructions can use. And finally, you need to update the PC, and depending on if the branch is taken or not taken, you will do it differently. So with that, this is the basic idea of the processor, right? So first of all, you have instruction fetch, and to fetch instructions from the memory, and then you decode the instruction and prepare the registers and feed the instruction into different parts of the computer, right? And then finally, you have the you update the program counter if necessary. In the very naive design, this is what we would probably do, right? So within a single cycle, we will have the instruction go through everything that we need to do. And in the next cycle, you get a new instruction in and have the instruction do something, right? So in this way, right, you can imagine your instruction execute timeline would be something like this, right? So everything is serialized and every instruction is executed back to back. However, there's no overlapping of that, meaning that the cycle time could be really long because each cycle you have to get this stuff done. Or on the other way, a lot of functional units were not functioning. So for example, maybe a quarter half of the cycle, you know that I have done this, right? And this part of the hardware could be yelled to other stuff to do, but you have to let them sit and idle, right? So that's not good. So we start to have the idea of pipelining. So the pipelining idea is that we have the instruction make partial progress every cycle, but because every instruction only to move through part of the processor, so the cycle time could be set really short. So it turns out that in each class cycle, we may just want the instruction to go through the instruction fetch stage, or the instruction can go through the from the instruction fetch to decode, and you can yield your fetch unit to fetch another instruction. And gradually, you can move your instruction to different parts of your hardware simultaneously, so that right now in this processor, you see there are 3 instructions going in. And when you keep moving those, so this is like an illusion that right now you have 4 instructions that your processor are executing. However, they are all on different parts of the processor. And at some point, if you can keep feeding the instruction, feeding instructions into the processor, then you will figure out that the pipeline would actually create an illusion that every cycle from the observer's perspective, right? If I'm the observer, I will see that every cycle, which is in which the cycle time is a lot shorter than the previous design, that every this short cycle, I can see an instruction being produced, right? So the same CPI, right? Because if you have each cycle generating 1 instruction, it's still the same CPI, but cycle time is a lot shorter. But with pipelining, you can make the cycle time a lot shorter, but the CPI is still maintained. However, this is just an ideal world. And in fact, in reality, we have 3 types of pipeline hazards that are preventing us from reaching the goal of CPI equal to 1. And these 3 types of pipeline hazards are structural hazard, control hazards, and data hazards. And structural hazard means that whenever you have 2 instructions, one to execute simultaneously. However, because remember, although we allow them to be, we allow multiple instructions to perform operations in parallel in a processor, but that constraint means you can only have 1 instruction at a particular functional unit. So if they are working on the same place, then that's not going to work out, right? So because the same hardware cannot serve on the same circuit, the same gate cannot serve for 2 different instructions simultaneously. So that's not going to work out. So that's structural hazard. And the second type is, remember, sometimes we have instructions like branch. So whenever you have a branch, there's no way for us to be 100% for sure what's the next instruction to fetch. In this way, your pipeline cannot be smoothly fitting instructions so that your CPI won't be equal to 1 in this case, because you have to wait. So that's control hazard. And the last type is data hazard, means that there is a data dependency between a later instruction and an earlier instruction. And because of the pipeline design, the instruction result cannot be delivered through, or say the execution is just so long that we cannot make the value propagated to the time that your instruction needs it. So a universal solution to this pipeline hazard is actually stall. By stall, we mean we let the early instruction to make progress first, and then the later instruction would just wait. So turns out that if you use the idea of stall, for this particular 6 instructions, it would take, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, at least 10 cycles to get those instructions finishes, right? And originally we said we want CPI equal to 1, but as you can see, the CPI is definitely going to be larger than 2. So that's not what we want, right? It's too far away from our ideal CPI. So we have to address those. And for structural hazard, there's no better solution than modifying your hardware, to be honest. So there are several ways of doing it. So you can definitely stall, or you can just make more rewrite ports in memory and registers, so allow more concurrent accesses. Or you have to split the hardware units. So for example, instruction data caches are now split in most of the processor design, so that you don't have to compete the memory bandwidth between instruction fetch, and which you have to have it happen every cycle, or some and you don't have to compete it with data memory access, which oftentimes would have conflict, or will have misses, or it will just interrupt the access of an instruction, which you definitely don't want it to happen. And the second type of hazard that we care about is called control hazard. And control hazard is actually more problematic than you could ever imagine. And I think through a few demos, you probably would know. And this table shows in a set of programs in spec 2006, 20%, around 20% of the instructions are branches, which means that if you have to stall every time, and if you have to stall for 2 cycles every time, your CPI would get 40% increase, even though it's just 20% of them. So a solution that we introduced in the class is called dynamic branch prediction. So the idea of dynamic branch prediction is, in addition to the original processor, we add this thing called dynamic branch predictor, which help us to predict the outcome of the branch, and then provide another program counter for the instruction fetch unit to use. So the basic idea of dynamic branch prediction is that we have to maintain the target address, which typically you have to get it through calculation, and also you have to you have to maintain a mapping table between a branch PC and its target, so that you know whenever I meet this program counter, this is probably the target. And then for the state, right? For the state, if you use a local predictor, you may have to attach a state with each branch PC, so you know when I see this PC, here is what I should predict. So that's the very basic idea of branch predictor. And you also need to get the outcome from the LOU, so that you will get the target PC updated and also get the state updated according to the branch execution result. So the very basic idea is a 2-bit local predictor that we introduced. And a lot of you are trying to memorize this, but that's not something I really recommend. Again, the big picture, right? The big picture here is, this is a local predictor. Means by local, it means that for each PC, we have such a state machine. But if you want to see the big picture of the state machine, again, it's nothing different, nothing but a 2-bit saturated counter. So what does that mean by a 2-bit saturated counter? The maximum value that a 2-bit saturated counter can express is actually 3, and the lowest number is actually 0. So the number would jump from 0 to 3 as shown in a state transition diagram. And we set a threshold, say 2, right? When it's larger or equal to 2, we predict the result to be taken. And if it's smaller, then it's not taken. And how do we maintain the saturated counter is that whenever we see a taken, we just increment it. And saturated counter means that if it reaches the maximum, then we are not going to increment it anymore. And the same thing, if we see a not taken, we decrement it, right? So saying that, if I'm currently at 0, and if the threshold is 2, it means that I need to see two consecutive taken to make the prediction taken. Or if I'm currently at 3, I have to make 2 consecutive non-taken to make it non-taken, which reaches 1. And if I am currently sitting at 1, right, it's a little bit awkward, right? If I have 1 taken, then I will move to taken state. But at the same time, if I get a not taken, I will have to move back to 1, right? So if you have a pattern like not taken, taken, and if you are currently at the value of 1, it's probably the worst because you are because at this point you are at this point saying that you are at 2, right? And because it's not taken, you go back to 1. But now you are at 1, but if it's taken, you go back to 2, right? So turns out that you are always predicting the flip side. So that's actually the worst case for this kind of 2-bit predictor, right? So these are the basic big picture of this 2-bit predictor, right? So of course, you can draw a state diagram and then you can list a table like this, which tells you exactly what's the actual outcome, and you will get 90% accuracy, right? You will conclude with 90% accuracy with this one. And for more complex cases, you can also expand a table like this, right? So remember, this is a local predictor. So local means that we have to train the state of each branch separately. So for branch X, right, and branch Y, so that's why we label branch X and Y separately here. It's only affecting the taken or not taken result. It's only affecting the state for X and Y here, right? So for its individual branch. So for the branch X, if we start at 0, 0, right? Because we never, if you look at the pattern here, right? It start with 0, so it's taken, not taken, taken, not taken, taken, not taken, right? And remember what I said. This is a 2-bit saturated counter, means that you need 2 consecutive taken or not taken to change your prediction. So it turns out it's not going to change your prediction in the best case. So if you initially in a 0, 0 state saying that I am predicting not taken in the very beginning, then it's not going to be brought up to predicting taken anyway, because you are always having this +1, -1, +1, -1 pattern, right? So turns out that you are only going to predict one direction. So the other direction, you will never get it right. So it's 50%. And for this part, right, because the pattern is always taken, right? So except for the last one. So you can say this is like 99% accurate with this, right? So this is the idea of local predictor. And but as you can see, the local predictor has its own limitation. So we have a global predictor in a way that we try to not predicting the branch result based on our particular branch outcome. Instead, I observe the history of all the branches and see if there is a pattern, right? So for example, if I have saying that if I have a code saying that if I have x equal to 2, if I have some cases like if it's x mod 2 and equal to 4, oh, sorry, what am I talking about? All right, if I have a case like x mod 4 equal to 2, and then another one saying that x mod 4 equal to 0, right? Then you can probably guess there is some kind of pattern here that if x equal to 4, sorry. Oh, this is not this is okay. This is probably what I want to say. So if I have an if statement saying that f mod 2 equal to 0, and another if statement saying that x mod 4 equal to 0, right? And you know, if something mod 4 must be equal to 0, it must be equal to 0 when it mod 2, right? Because these are correlated. However, from your local predictor, you won't see this correlation. So that's the basic rationale behind the global history register, is that sometimes the result, or say the outcome of other branches, could provide insights for the other branch. So it turns out the global history predictor is trying to establish this kind of relationship through observing the history. So when it makes prediction, it takes the current history register and see what's the state. Like when the last time we see this pattern occurs in our execution, how do we trend? So for example, how should we predict? And for example, like this now, we have the value 4. So go through 0, 1, 2, 3, 4, right? And then if it say it's 1, 0, you will predict it to be taken. And if this is the current PC and this is the target, then with it predict taken, I will modify the PC to be this one, right? So that's the idea of global predictor. So with global predictor, right, for this one, you will definitely see, even for this local one, if the last execution result is 1, then the next time will be 0, right? And if you want to capture this pattern, right, it's not to, it will be like taken, taken, not taken, 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 not taken, taken, not taken, right? So you will see this value, this pattern goes on, right? And as you can see from this table, right, it's indeed the case in a way that you will see the actual outcome will be like that. And if you establish a global predictor, you will see after we get it well trained, right, the same pattern could be able to be predicted through that. So based on that, if you understand the rationale behind both predictors, right, here's the big idea of our branch prediction. So for a 2-bit local predictor, it's actually consider each branch separately, maintaining the state of each branch. So no matter what other branches behave, it won't affect its opinion on a single branch. Very professional, to be honest, right? And however, but the thing is that you will also sacrifice the benefit from the global history as well. And if you have a 2-bit counter, then what turns out is that it also means the predictor will stably predict one direction if the pattern appear twice or consecutive pattern appear twice or more regularly, right? Another one which we introduced is called global history, right? States are associated with the history of the branch outcome, regardless which branch generates the result. So for this one, totally ignore which branch generates the result. And it's effective if you have a history pattern that could be captured by history registers. However, if your history if it takes a long history to have a pattern, repetitive pattern, and your register is really short, it's not going to work out, right? So let's revisit the code again, right? And let's look at the history. So if you see the history of each branch saying X, the pattern is taken, not taken, taken, not taken, taken, not taken, taken, not taken, taken, right? And repeatedly, right? And you know, for 2-bit local predictor, as I said, right, the pattern is not, the same result doesn't appear twice or more. So the best it can do is actually 50%, right? And for this one, because it has been more than 2, right? So it can get 100% for this one. And for a global history, right? If you look at the pattern, right? The repetitive pattern is only 4-bit. So if you have a 4-bit history, it will work out. Right? Okay, look at another code, which I simply modified this to be 10. Then local history 1, right? This is more than 2 already. So turns out the local history 1 worked really good, except for the rare case here, right? So 90% accuracy and almost 100% for the next one. And for the global history 1, the pattern is actually this long, right? So you definitely need something to have this correct, right? So although right, the pattern here seems pretty well behaved. So everything like this, the global history could make a good prediction. However, for this one, that's really not something the global history 1 could help. So the global history 1 will still miss for this particular case. So that's why if you review the class question we have on this particular pieces of code, we say the performance of these 2 predictors on this pieces of code is about the same, because no one can do a good job on this rarely happen branch. And hopefully this would give you a better idea regarding, hey, how can I figuring out the performance of my branch predictor, right? So again, the big picture, right? The local history is predicting based on the local history. So if your local history seems to be easy to predict with a 2-bit counter, like the same thing appeared twice, more than twice, right? Then you know it's going to be your local predictor is going to capture it. Or if you have a history that's like this 2-bit history looks really good, right? So for the global history predictor, the 2-bit or any history that's longer than 2-bit can make this work. However, if you say I really want to predict correctly on this one, it's impossible. So these are the stuff that you have to keep in mind. And again, this is the importance of remembering those big pictures of how predictor works. And most of the time, our modern processors, we know each predictor has its advantage and shortcoming. So for each particular branch, we would have a predictor to judge which is the best predictor for this particular branch. So that's how we perform prediction. And the branch predictor in modern processors are very complex, and it could be one of the most popular. It was the one of the most popular research topics in by the end of the last century in computer architecture research. And turns out that nowadays people are using a lot of fancy predictors in commercialized products. For example, the latest AMD or Samsung product, they use perceptron-based neural branch predictor, which is amazingly complex. But for us, being a programmer, it's more important for us to figure out how branch predictor would affect our programming. So remember, right, in the very beginning of the quarter, we have this demo. And now you should already figure out that the reason why after you sorted the data, the performance becomes a lot better is that after you sort the data, this branch X, which we marked here, becomes relatively easy to predict, because no matter it's before or after the threshold, it just changed the direction. And once you change the direction, it's going to has the same direction till the end of the execution. So what does that mean is that no matter you are using a local predictor or a global predictor, for this case, right, you can imagine once you fix the direction of this branch, then no matter it's a local global predictor, they will predict very good. So this is worth doing if you can sort the data ahead of time when you are, and if this is the most time consuming part of your program. And I think we made it 5 implementations at the end. Do I have this? Wait, give me a second. No. Okay, so we will talk about this later, right? But if you look at different implementation, definitely branch has a lot of effects on that. And in fact, right, to solve the control hazard, branch prediction is the hardware solution. But as a programmer, there are more things you can do. And now, with data hazard, that's the third type of hazard that we have to deal with every day. And data hazard is erased from data dependency. So it means that an instruction currently in the pipeline cannot receive the logically correct value of execution, meaning that it doesn't mean it cannot receive a value, but it just cannot receive the right value that generates the result that the programmers want. And a lot of us are confusing the idea of data hazards with data dependency. So data dependency is the pure relationship between instructions that we have in a program. So whenever an output of an instruction is the input of a later instruction, there is a data dependency. And data dependency may lead to data hazard. However, not necessarily means that a data dependency would lead to data hazard, because it's only called data hazard when there is an awkward situation that the pipeline cannot make progress because of the data dependency. So here I put a syntax of move-L, so that because I feel a lot of us has already forgotten the x86 syntax. So a few syntax you need to remember is that if you have a quote outside of the register name, it means it's a memory location. So if you are moving something from a memory location to a register, then it's a load, right? And if you are moving something from a register to a memory location, this is going to be a store, right? So this is the code of swap for implementing this swap. And although a lot of people will think this is the naive implementation of the swap, but it only incurs 2 data dependency of the compiled code. However, this one looks really fancy, and in fact, a lot of books or people will ask you to answer this, like, can you use only 2 registers or 2 variables to or say 2 memory locations to perform the swap? The answer is, of course, yes, but why bother doing that? Because it's not going to work out very well in terms of modern processors design. So in modern processors, right, if you look at the syntax, the generated code, it's this sequence of code. And remember, the syntax of XORL is that if you get 2 registers, the later one is the destination. So it's actually computing B equal to A exclusive OR B. So B itself serves as both inputs and outputs. And if this is a memory location, you have to get in additional memory operations involved. So this is actually a very low latency operation, because thinking about this, you have to compute the result of this, you have to fetch this from the memory, and then you perform exclusive OR, right? And memory is already slow, and then one additional one for exclusive OR. But let's just look at the data dependency. And for this one in particular, there are 5 places, or say 5 pairs of instructions that we will see data dependency, because especially it's all on EAX, which create the case of data dependency. So for this particular one, if we try stall for the origin, the most simple and naive version, we will see that there are cases where we already have the value of EDX already, but just because the design of our pipeline doesn't allow us to get the value at a time we want it, even though it's already generated by the M2 stage, we still cannot consume it. So it increased the amount of stall we need. So the second solution, which is the solution that most of the processor would take right now, is called data forwarding. And for this class, I don't want to make this too complex. I just want to let you know that modern processor has the capability to forward the value to other functional units whenever you need it. So the good thing about this, right, for the previous case, you only have to stall for one cycle because of this and this. However, for the fancier version of the swap, right? As the exclusive OR takes longer time to generate the result, and the memory also generate the result for later instruction back to back. So it turns out there are 3 places, or say 3 pairs of instructions still cause the data hazard to occur, meaning that at this time, when we want the result, it's not ready, so we have to stall one cycle. At this time, we want to execute this one because even though there's no one occupying the memory unit, but we cannot because we have to wait the exclusive OR to complete, right? So it turns out for this one, we have 3 places that doesn't allow us to make progress. So this is why this kind of swap operation is really inefficient in modern pipeline processor compared against the simple and naive implementation. So now the question is, even though we highly optimize our code, we still have the big question mark here. Is CPI equal to 1 our ultimate limitation? So a solution, the answer is definitely no. So in fact, every of our modern processors are now so-called superscalar processor. So the idea of superscalar processor is that we have so many functional units. If we can only see one instruction at a time, we are going to miss out the chance of fully utilize those functional units. So if you really want to utilize multiple functional units concurrently, then the solution is that you have to fetch the code and be able to issue, means that put more instructions into execution at the same time. So in superscalar processor design, there are 2 parameters. One is the fetch width, meaning that how many instructions can the processor fetch and decode in each cycle. And also the issue width, how many instructions can the processor put into execution at any cycle. So the idea of superscalar processor is this, right? It's not too different from what I saw, what I drew before, but I just make 2 arrows here, meaning that I can decode and fetch 2 instructions at the same time. So for this particular pieces of code, right? If you can fetch and decode instructions at 2, ideally we want every cycle we can have 2 instructions into execution. However, there's still a problem here. For example, for this one, it has data. For instruction 3, it has data dependency with the first instruction. So even with data forwarding, we have to wait here. And for this compare instruction, because we only have one execution unit for ALU operations, like comparison, because comparison is essentially like a subtraction. So it will share the same ALU as the addl instruction. And this is called structural hazard, right? In fact, so we do have a structural hazard here that we have to stop this instruction. So it turns out, even if we have a perfect predictor, we are still not able to fully utilize our pipeline in this way. However, if you pay attention to this instruction sequence, you will figure out for instruction 4, it doesn't depend on any value generated by 3 or 1. So in fact, as long as instruction 2 finishes, instruction 4 should be able to execute. And in fact, at this point, instruction 2 has finished it. And no one is using the functional unit. So if we can move instruction 4 earlier, then we can potentially move this, we can potentially further increase the utilization of our functional units. So if you look at the theory or say the policy of execution, in fact, right, whenever your inputs are ready, you should be able to put an instruction into execution. And whenever there is a functional unit is available, you should be able to execute the instruction. Whenever you know what you want the instruction to do, you should be able to execute the instruction. So if all these three things are satisfied, why not put the instruction into execution? So that's the whole idea of modern processor design in terms of dynamic instruction scheduling and out-of-order execution. So the idea of dynamic scheduling and out-of-order execution is that we want to execute instructions whenever we have data dependency resolved, whenever there is a functional unit available, whenever the instruction is decoded. However, if you practice a little bit, you will figure out that for this pieces of a code, we are not allowed to because there are some false dependencies preventing us from reordering those instructions. And these false dependencies are mainly from the fact that we have limited amount of registers. So if I can rewrite the code a little bit to use more registers, then turns out that all the false dependencies would be gone. So here comes the idea of register renaming and speculative execution is that we provide a set of physical registers and a mapping table between architectural registers to physical registers. Whenever there's a new output, we allocate a new physical register. And this way, we would be able to eliminate all the name dependency and purely based on data dependency to schedule our instructions. So, however, if we want to keep the pipeline filled, we definitely want to be able to schedule instruction across the branch. And the branch prediction could be highly accurate, but there are always exceptions that we cannot make the branch predictions perfect. So we need to preserve the capability of flushing instructions still. So that's why modern processors also have a reorder buffer to help us fill that. And with that, register renaming, right? Then this is the overall picture of modern superscalar processor with dynamic scheduling capability is that after decoding instruction, we have the register renaming logic that rename the instruction to physical register and put them in a queue. Whenever it's ready, we put them into execution. So previously, we have tried to use pipeline diagram to explain what's happening, but I don't think that works out pretty well. So last night, I was trying to think if there's a better way to help understanding. I don't know if this is going to helpful, but that's the best way I can think of for now. And if you have better suggestion, let me know. So I think maybe there's a way we can think about it. So first of all, the horizontal axis of this table, or say the column, each column of this table, represent different stage or functional units of a superscalar processor. So for example, if I have a superscalar processor with fetch unit, decode unit, renaming unit, and it takes 2 stages to finish a memory operation, it takes 1 stage for execution. But remember, because we want to avoid the structural hazard at the write back stage, so we force execution and branch instruction to stay as the same number of stages as memory instructions. So that's why I put this 2 dash stages here. It doesn't mean that the instruction needs execution. It just means that the instruction cannot be written back or commit because right now we have to prevent those structural hazards. And if we have 2 issue processor, it means that only 2 of the functional units, which is the, or say the first stage of each pipeline or functional unit pipeline could have instructions. So here is another way that I think could help us understand the scheduling of register renaming. So in the very first few cycles, it's easy to tell that we just keep fetching two instructions into fetch, decode, and rename stage. And interestingly, in the fourth cycle, right, we can check the first instruction. The first one is a move instruction. The second one is an LU instruction, and they don't depend on each other after register renaming. And you might think, well, they both use RDI, but this RDI here is only as the source. And this RDI here is both source and destination. However, remember, with register renaming, the destination will be renamed to a different register. And and if you draw the data flow diagram, because this is the source, so it doesn't really have a data dependency with the second instruction. So if they don't have data dependency, if this one is not waiting on anyone, they can be both executed at the same time. But this instruction, because it's a memory instruction, so it will take the M1, and this one will take the execution part. Now, for the next cycle, I can fetch another instruction, another set of instructions. And again, remember, only two of the instruction, the stage, only two of this three can have instructions in there. And in the fifth cycle, the first memory instruction is going to the second part of the memory execution. And so if you have a new memory instruction that is available for execution, you can put it here. But at this time, let's examine the instructions we have. For 3, it's depending on the value of ECX, which is still in a pipeline. So we cannot have 3. And for compare instruction, it does depend on RDI from 2. But for 2, it's already done, right? So then you can definitely forward 2. Well, I think I missed 2 here. So you can definitely that 4 in execution. And in the next cycle, right, 4 has free up the execution. So you can definitely put 3, especially at this time, the ECX is already generated by 1. So 3 can be here, and 4 is now in the idle stage. Let's call it idle stage now. And 2 has finished its work, so it could be written back together with 1. And at this time, right, because this is not an issue slot, right? Because this is already an idle slot. So even though there is another instruction here, but it doesn't affect our capability to issue one more instruction. So 5 is available after 4 finishes. So you can actually put 5 here. So if you keep drawing this one, right, at some point, keep drawing, you will figure out that once you fill the pipeline, every cycle, we are actually generating outcome for 2 instructions. So for this pieces of code, if I have register renaming, I can actually make the CPI equal to 0.5, which is the best you can do with dual issue pipeline. However, and also it can still use the data flow analysis, data flow graph analysis, as we previously mentioned in the class, because that's actually the basic idea how we execute instructions in dynamic out of order execution pipeline. And the reason why I invent another representation is that a lot of us are confused about, oh, like for some instruction, why can't I execute this earlier, like this 6, right? Or why can't I move it up? And the reason is just because we have only 2 issues, right? But if you have this in the previous representation I have, you will figure out that the reason why I cannot put 6 into execution at this time is just because we already used 2 of our issue slots. So you cannot have anyone here anymore. So this is the benefit of another representation. But both representations should be equivalent if you want to see the performance of your code. So it turns out if you use data flow graph analysis, you will see that the CPI is also equal to 0.5. And So another question we have is that how about linked list, right? So this is the code that I have for linked list, and if I use the same analysis methodology that I introduced today, you'll figure out that for the linked list one, the CPI is actually pretty bad, right? So for this part, right, on average, we cannot commit. This is 10.9, right? So you cannot you can only get like 5 instructions within 4 cycles. So your CPI is close to 0.8. And if you draw a data flow diagram, you will also see the same thing, that your CPI is almost like 0.8. And one thing I do feel is a little bit more difficult to judge from the previous representation is the critical path of its execution. So if you draw the data flow graph like this one, it's easy to tell that this is the critical path of execution, because it looks like you can expand the same graph again and again, right? So you can tell who is on the dependency chain, and it turns out it's going to be these 2 instructions, and all the instances generated from these 2 instructions. And going back to the C code is reflecting to this statement, right? So this is how you can learn a lot of things from this graphical representation, and none of this will require you to draw the pipeline diagram. So in the final, all what I want is probably asking you about, like, okay, can you tell what are the critical paths of the problem, and can you tell what's the average CPI of this? So if you can have some representation like this, or if you can explain, well, why this is the critical path, right? And because there's a data dependency here, and for example, like instruction 2 and 6, we have to wait for 3 cycles because of what? Then it's probably good enough for your answer. So right now we have learned quite a lot. So to solve the pipeline hazard, we have learned structural hazard, we have learned control hazard, we have learned for data hazards, stalls, data forwarding, compiler optimizations, or dynamic scheduling. They could all help. However, compiler optimization is pretty limited because compiler cannot predict the future. So loop unrolling doesn't always work if we don't know how many times we are going to execute the branch. Compiler doesn't know if the memory access is going to behave well or not. And the other thing is that compiler can only see architectural registers, but cannot utilize those physical registers that a modern processor provides. And compiler optimization cannot be adaptive to any microarchitectural changes. For example, your pipeline gets deeper, or if you have new feature from the pipeline, you have to recompile your code. And after you recompile the code, it probably won't work with old processors. So it's very limited in practice in a lot of cases. So so that's why we need this hardware optimizations. And in fact, modern processors like Intel processors or AMD processors, they all have the hardware optimization that we mentioned. So if you really want to fully utilize the hardware resources we have right now, it's really important that we need to learn how can we figure out the critical path of your program. And based on that, if the critical path is falling on memory instructions, can we make the memory behave better? Or can we make it more cache friendly through tiling? Can we use better data structures like hash or arrays to avoid hard to predict data structures? Or if it's on branch, can we sort the data? Can we unroll the loop? Or can we just don't branch, right? And there are still cases like, okay, if I am working on instructions like mod instructions, can I replace them with something else? And also, processors typically have multiple functional units. So can I hide as many instructions as possible under the critical path, since only the critical path instructions affects the performance? And try to use as many different functional units as possible. I think in the lab, Let 5. There are lots of examples like that. And also, modern processors has many accelerated instructions. Can we use them? So for this particular pop count program, we have explained that in very detail. If you don't remember, let's go back, probably go back and look over those YouTube videos. But the D version is the fastest, and B is better than A because we are able to eliminate some branches with manual unrolling. And for C, we use the idea of lookup table to reduce instructions, but the lookup table must fit in the cache. Otherwise, if your table is really big, then it's going to be worse. And for D, it eliminates all the branches because it allows the compiler to automatically unroll and also use the lookup table to reduce the amount of instructions. And E is actually the worst because we have a lot of hard to predict branches. So this question is very interesting and very useful in your future because it tells you what are the code that could be performing better, what are the code that would perform very bad, right? But so that's the stuff we have learned. But we still have the problem that in a lot of cases we have code that has a lot of has very low ILP. So if we cannot squeeze sufficient amount of instruction to execute on a single processor, simultaneous multi-threading says that we can provide a new mechanism for you to use instructions across multiple hardware threads, multiple programs at the same time. And to support that, your processor could be, you still need to add more things into your processor, and essentially the program counter and the ability to fetch more instruction and decode more instructions. So that, because I get to see instructions from another program, so I can use them to fill the pipeline that is underutilized. However, because you are sharing the cache, because you are sharing your pipeline, so the performance of a single thread could get affected. But it's only about the throughput. And in fact, thinking about your system, if you check your Linux system or any of your operating system, you will figure out simultaneously you have thousands or hundreds of threads to, or say hundreds of processes to execute concurrently. So simultaneous multi-threading is really useful in a way that since we are now in a world of multi-programming, so it's easy to find thread to execute. And however, even with simultaneous multi-threading, it's still a single processor, single wide issue pipeline. So if you want to speed up the execution of that kind of processor, the only way to do it is to make your frequency better or make your microarchitectural design better. But turns out you still want your frequency to be better. But according to our theory, with double the frequency, you are going to see cubical relationship with the frequency you increase. So turns out you might get 8 times power consumption than your baseline design. However, if you just double the number of cores, it's just getting more transistors within the chip. So turns out your power consumption only gets doubled. So an analogy would be you can produce the left-hand side processor with high frequency, high power consumption, but you can only get limited amount of thread instruction level parallelism from programs, or you can build the right-hand side one with more processors, each with narrower issue, allowing you to exploit more concurrency from your programs. So turns out modern processors take the right-hand side design in a way that they are all multi-core processors, which you have shared cache and private cache. So the concept of chip multiprocessor is that we duplicate the processor core and make them connected to a shared cache. However, and these two architectures both have its own strengths and disadvantages. So definitely you have to think of carefully about which one is the better. And another thing that's also important to remember is that both architecture cannot work without software taking advantage of the fact you have multiple concurrent hardware that can put into execution. So it's really important that your software have to fully to understand how the hardware works and utilize them. So there is a popular multi-programming model called thread programming model. They consider each core as a unit of a thread or process execution, and they consider all the cores are connected to a shared virtual address space. But you know that's not a fact. In fact, each processor has its own private cache. So that will be problematic in a way that others cannot see each other. So that's why we need the coherence protocol and consistency protocol. And it will guarantee all processors see the same value at the same time with the coherence protocol. And for the consistency protocol, it would require all threads to see the change in the same order, which further help us to guarantee the correctness of your program. So to maintain the consistency and coherency is that you have to expand your value bit in your cache to allow them to accommodate the state that's new from your coherence protocol. And you don't have to memorize this protocol. All you need to do is that your processor need to maintain coherency. And sometimes it will cause the issues like false sharing in a way that, like this program in particular, some of your elements, let me miss that slide. Okay, so so for this particular problem, you have to remember your cache is maintaining states by block. So if you interleave your data access among multiple threads, even though I'm not actually accessing this one, because of this one is invalidated, the whole block gets invalidated. So the miss rate will be really bad. So you definitely need to optimize your code to make sure that there is no sharing or limited amount of sharing between your threads. So that's why thread programming is hard. And thread programming could be even hard, like for this particular problem that we have shown, or the demo we have shown in the last lecture, that every value listed here could be possible for these two pieces of code, even though you probably just want the final answer to be 1, 1. And the reason is because we have out of order scheduling. So even though 0, 0, this kind of case that looks least likely to happen would happen. So if you want to reduce the problem, you really need the consistency protocol to help. However, modern processors only support very limited amount of consistency support. So it turns out, even though I'm able to insert fence instructions, which means that it requires A equal to 1, this statement must happen before this one. But because those threads, like thread 1 and 2, they may not be executing together. So for example, if I launch thread 1 a lot earlier than thread 2, right? Even though I have the fence here, I can still execute like A equal to 1, X equal to B, B equal to 1, Y equal to A, right? If you are executing thread 2 a lot earlier than thread 1, then you are end up getting B equal to 1, but because there is a fence, Y equal to A equal to 1, X equal to B, right? So you will execute in this series, right? So what will happen is that the only thing that we will guarantee is that 0, 0 won't happen. Other than that, there is nothing could be guaranteed, right? So even with fence instruction, programming in multi-threaded hardware is still problematic. In addition to CPUs, there is an alternative and increasingly popular architecture for people to do parallel processing. That's the GPU. And the GPU's idea is really simple, is that we just put a lot of ALUs, and these ALUs can perform the same operation within a single SMX, like string multiprocessor. So the programming model of GPU is that I can feed a vector of data into vectors of data into the same SMX, And all the ALUs within this SMX, they will perform the same operation. So like this one can do plus, this one can do minus, this one can do multiply. But if you remember how big is each one, it might have like 192 cores. So you can compute on 192 numbers, pairs of numbers together. So that's the GPU architecture. So you can imagine like this one, we have we have 13 SMX in it. So you can have 2,000 threads computing on the same thing, on the same operation at the same time. However, you can also imagine if your data is not vectorized, it's not going to help. And the other thing is because this GPUs are called GPUs because they are designed for graphics. And even with 120 frames, you can still think that I can tolerate like 8 milliseconds of latency, right? However, if you think about for microprocessors, we are talking at a nanosecond scale latency. So the latency that the GPU can tolerate is a lot longer than the CPU. So if you today you are really having like latency sensitive, latency critical tasks, it's probably not a good idea to use GPU because sometimes your latency could be sacrificed because of that. And right now we are in the era of dark silicon where we don't see the performance of CPUs increasing. And the reason is not because of the Moore's law not allowing us to have more circuits. And in fact, you can have more circuits, but the result will be like what happened in our GPU nowadays is that NVIDIA's GPU are able to put more transistors in there. But if you look at the power consumption, it's actually significantly increased. So this is not possible. This is possible for GPUs, but probably not possible for processors. So that's why we start to see a lot of solution to deal with that. And in fact, this trend is causing a problem called dark silicon that because the transistor power is not decreasing as it used to be. So it turns out that right now, if I can only power on the chip with the same amount of power, a lot of my circuit could not be functioning. So that's why it's actually a constraint of modern processor design. So if you look at modern processor, typically, like if I want to have more cores, I have to lower my frequency so that I can maintain similar level of power consumption. Or I have to design application-specific ICs like TPUs to accommodate that. All right, so this would probably conclude our most of the stuff that we learned. And at this point, I would like to invite all of us to show your face through camera